Thank you. Thank you very much, Joe. I'd just like to say thank you very much for the support which you've given to the ICIC in setting it up, and that's been very much appreciated. Joe, as you've probably guessed, I've not been here all that long, and in fact, Joe said, you haven't been here very long, so I wonder, you might be wondering why there's this big photograph of me on the screen, and it's because Joe said, well, you haven't been here for very long, could you bring some photo ID? So, so that's it. I'm also very pleased that Malcolm Longhair has come from Cambridge to give the vote of thanks. He's been an inspiration to me all through my career since being an undergraduate at Cambridge, when I had the pleasure of doing a project with him. And in fact, I've got a letter that he wrote to me in 1980 when I was moving, came across various bits and pieces. He gave me a project which was fiendishly difficult, in which some of the reading materials were in Russian. Learning Russian was not one of the learning outcomes of the project, as we would call them today. So he kindly translated the relevant piece for me. But you can see it was a slightly different era because the communication between student and supervisor was by letter, which I think, judging by it, presumably had been dictated to the secretary and typed by the secretary. So it was a slightly slower form of communication than the instant emails that we have today. So tonight's talk concerns Big Bang cosmology, and this slide shows you essentially the whole of the history of the cosmos in one slide, starting with the Big Bang on the left-hand side. And time goes from left to right, and you see the development of the universe from the initial rapid expansion, which we believe took place in a period called inflation, during which time small fluctuations, quantum fluctuations, are thought to have been generated. And those fluctuations grow over time to form the structures that we see today. And you can see, going from left to right, you can see the formation of the structures. And indeed, we can see something like this picture today because of the finite speed of light. Then the further you look, then the further back in time you look. So you can see a picture that looks very much like this. And this is an expanding universe. Everything is moving apart from each other. And the subject of the talk today will be just to give you a little bit of a flavor of the sort of statistical analysis that we do on most of the things which you see in this picture. Nearby galaxies here, the light that's left over from the Big Bang, which is on the left-hand side there, and the distant galaxies, which you see on the left-hand side. And one of the things you have to deal with is that when you look at distant galaxies on the left-hand side of this, then the light that you see has passed through all the stuff that's between the left-hand side and you. So let's just briefly review what we know about the universe and start with what we know about the amount of ordinary matter in the universe. And if you go right to the left-hand end of that diagram and ask what was happening a few minutes after the Big Bang, the universe was very hot and very dense, the sort of conditions not very dissimilar to what you get in the centers of stars. Many collisions taking place at high energy between nuclei, and building up light nuclei through these collisions. And you can build up a few of the light elements this way, and you can detect those today. And obviously, dependent on the number of nuclei that you have, that controls the number of reactions which take place, and controls the yield that you get at the end, how much of each of the light elements survives. After a few minutes, the universe has expanded and cooled so much that these processes have essentially stopped. But you can get hydrogen, you start with hydrogen, you get helium and heavy hydrogen and so on, and also traces of lithium. About 1 part in a billion is converted into lithium. So the lithium that you get in your watch batteries, most of it was created a few minutes after the Big Bang. And you can see that here Energizer have claimed that this is the world's longest lasting, and you can't really argue with that. The lithium has been around for 14 billion years. but do pay attention to the fine print that you have to use it by 2026. So what we conclude from this is that the abundances of the light elements tell us that actually there's not very much of this ordinary matter in the universe, and only about 5% of the total mass density or the total energy density of the universe is in the forms of matter that we know on Earth. So is there anything else? Well, we've known for a long time, since the 1930s, that there is something else, and Fritz Zwicky was the first to postulate that there's some other matter in the universe that's not in the form that we ordinarily come across, by analyzing the Coma cluster, which has galaxies, many hundreds, even thousands of galaxies in it, and they're moving at great speed, many of them in excess of 1,000 kilometers per second. And at that speed, they should just drift off into the rest of the universe. But something keeps them in place and keeps the cluster bound to itself. And in order to do that, the only force which is relevant is gravity. But to get a strong enough gravitational force to keep these things bound to the cluster requires a great deal more mass than you see in the visible light from the stars in the galaxies that you see there. So that was the first indication that there's something other than ordinary matter observationally. And we're refining what we know about the dark matter. There are searches in this department for dark matter, or involving people in this department. But one influential object from astronomy, which has helped tell us about the form of dark matter, is a thing called the bullet cluster. This is a pair of clusters of galaxies which have passed through each other. They've had a collision that's where the galaxies have passed through each other. And what's happened is that the galaxy clusters, which have a lot of hot gas in them as well as the galaxies, have left the hot gas behind. The hot gas has collided and shock heated and got left in the middle. That's the pink stuff. The galaxies themselves in the image have passed through. They're basically collisionless. The chances of having a collision between pairs of galaxies is very low. But the interesting thing about this picture is that you can deduce where the dark matter is by looking at a phenomenon called gravitational lensing, which I'll talk about in more detail later. But this tells you that the dominant matter in these clusters is given by these blue patches, and you see that the blue patches are centered where the galaxies are and not where the hot gas is. So we deduce from this that the dark matter is essentially collisionless, that it has passed through along with the galaxies and not got stuck in the middle where the gas is. We don't know a great deal about what the dark matter is. There's various things that we do know, that it doesn't interact except possibly weakly. So we've got ordinary matter and we've got dark matter. As Bob Geldof might have said, is that it, or is there anything more? Until the late 1990s, the indications were that perhaps there wasn't anything more, but in the late 90s, people made observations of large numbers of this object. This is a supernova explosion. It's a star which has come to the end of its life and has exploded, becoming extremely luminous. And the nice thing about these things is that they're so bright you can see them to very large distances. And so you can see them at earlier times in the universe. The more distant ones you see as they were many billions of years previously. So what do these things tell us? Well, if you plot a graph of their distance against their redshift, so somewhat loosely speaking their recession speed, then the more distant galaxies, more distant supernovae are moving away faster. And this is Hubble's law. But the interesting point about these things, maybe I'll look at on this picture over here because it's slightly clearer, is that if you look at the data points from the supernovae, that they lie slightly above the middle line that you may be able to see on here, the white line. Now, the white line corresponds to the distances that you would expect to see if the supernovae didn't slow down or speed up. If they went at constant speed, then you would expect to find the supernovae lying on the on the white line, the middle of these three. In fact, they don't. They lie above the line predominantly. If you look down here, it's been flattened out, so the white line is it's horizontal. And most of the supernovae lie above this line. I prefer to think of this as being not that they lie above the line, but they lie to the left of the line, which means that when we look at them, and these are supernovae which we're looking at as they were in the past, then they were then expanding at a speed which was slower than we would expect if they hadn't speeded up or slowed down. So they were traveling slightly more slowly than we expect, and the implication of that is that they've accelerated, they've speeded up. And that was a great surprise, because we tend to think of gravity as slowing things down. If you throw something off the Earth, then it will slow down and fall back down again normally. So to have a universe where the objects in it are expanding, but they're not slowed down by gravity, but they're actually speeding up, was a great surprise. And this has revolutionized cosmology in the last 15 years or so. So the question then is, how can you get acceleration? So gravity will tend to slow things down, so we have to find some way of getting the universe to speed up. And in fact, one answer is an old one, which Einstein introduced in the early years of the last century by modifying gravity to make it push as well as pull. And he introduced into his equations a term which is called Einstein's cosmological constant, which he later said to Max Born was a monumental blunder. Turns out that may not be true. It seems that he might have been right all along. The reason that he introduced it was that he was trying to create a universe, theoretically, a universe which was static, which was not expanding or contracting. So in order to counterbalance the force of gravity, which is likely to pull things together, he had to change the law of gravity to have a component of it which pushed, so they could balance. This was indeed a big mistake. This was done before the expansion of the universe was known. So he missed the opportunity to predict that the universe was not static. He could have predicted that the universe was expanding or contracting. And I think it's no exaggeration to say that if he'd done that, then Einstein's name would be a household name today. He would be well known everywhere. So this cosmological constant has the symbol lambda, and it completes the major constituents of the universe. Now, we'll see later that we can reinterpret lambda as being something else, which we'll call dark energy. And the components of the universe are the major ones are ordinary matter, making up only 5%, dark matter, probably some form of particle in abundance, and this mysterious dark energy, which has the effect of pushing the universe apart. So how does a universe like that behave? Well, if you put the universe into a computer and let it run, the forces of gravity, including the repulsion, so this picture should really be expanding with the universe, but the expansion has been taken out. But what you can see is that over time, the dense parts of the universe are getting denser because their gravity is pulling material in from the surroundings. And you see that the universe develops a very beautiful network of filaments and voids and high-density clusters in the middle. So that's how we think the structure that we see today has come about. But we can look at this in more detail, and this is where statistics can help us to decide what's happened. So if you look at the background to this slide, then what you see is observed data from a telescope in Australia, and each dot here is an individual galaxy. This is huge scales, hundreds of millions of light years across, even thousands of millions going from one side to the other. And what you see looks broadly similar to what you saw in the video, that there are these void regions, there are filaments, and high-density regions as well. But there's a question, really, as to why these void regions are dark. So there's two broad possibilities. One is that they're dark because the matter has streamed out because of gravity, as we saw in the video. But another possibility is that those regions are dark because galaxies don't form in those void regions. And it could be some combination of the two. It could be that galaxy formation is not very efficient in those regions. Now, it's important to know which of those is the right answer, because what we really want to know is what the dark matter is doing. As you've seen, the dark matter is the dominant matter component. Let's forget about dark energy for the time being. There's much more dark matter than luminous matter. So the dark matter is what theoretically we can predict. We can predict the properties of dark matter much better than we can predict the properties of galaxies, because galaxies depend on how galaxies form, how stars form, a lot of complicated astrophysical processes. But dark matter is predominantly just controlled by gravity, so that's relatively easy to predict. So we can use statistics to distinguish these two broad models. So in the top right is a computer simulation where the voids have been emptied by matter, dark matter and ordinary matter, flowing out, like you saw in the video. And the ones on the bottom are what you would expect to happen if galaxy formation was inefficient, was basically turned off in some of the lower density regions of the universe. So this is a highly evolved state where gravity has been acting for a long time. The alternative is that you start off with a density of matter which is much more uniformly distributed, so these blue regions have a lot of matter in them. They haven't had time yet to empty. But if you turn off galaxy formation in the blue regions, then you end up with a distribution of luminous matter, which looks like this. So these two pictures are different. It's harder to distinguish them when you sample with dots from a distribution like this, but you can use statistics, and we used a statistic called the bispectrum to tell us which of these pictures was the correct one, and it turns out that it's the top one, that the matter in the universe, the dark matter in the universe, is distributed very much like the luminous matter, which means that the voids in here are really pretty much devoid of all forms of matter. And that's very useful because it means that the galaxies that you see are tracing quite faithfully, on very large scales, they're tracing quite faithfully the distribution of the total matter. So you can use galaxies as a proxy for what the matter is doing. That argument needs to be refined if we do things in great precision, but that's the basic picture. So that's the matter in the universe. The other very useful form of energy that we can use to probe the universe comes from the light that's left over from the Big Bang. So this is the temperature of the so-called microwave background radiation across the sky. The sky's been unwrapped so you can see it all. And what you see is that the temperature of the microwave background is not quite uniform. These different colors correspond to changes in temperature, variations in temperature of about 1 part in 10 to the 5, so tiny fluctuations. And these, we think, are the result of quantum fluctuations in the early universe. This is observed with the Planck satellite recently, and you can compare what you see with the theoretical predictions from models where quantum fluctuations were created in the early universe and have evolved over time. And in one of the most fantastic diagrams, I think, in cosmology, you have this agreement between the theory given by the line and the data points given by the red dots. Now, there's a certain amount of freedom in the theory. It depends on the matter content of the universe, the expansion rate, the amount of ordinary matter, and so on. So you can adjust the theoretical curve a bit, but the fact that there is such fantastic agreement is a triumph of the scientific method. And this really is the biggest challenge to any non-Big Bang theory, to find a way to explain those red dots without having something which looks very much like the Big Bang. So let's just go back to where we'd got to. The assumption is that these fluctuations in the light were created very early on, and if the model of the universe is right, then these should be essentially random fluctuations. For the specialists, a random Gaussian field. So these fluctuations should be random. I'm just going to use the term rather loosely to mean just the random fluctuations that you get from quantum fluctuations. So these things should be very, very close to random. The deviations from genuine randomness are expected to be at the level of 1 part in a million or so. So we can test whether that's the case by looking in detail at the statistical properties of the light. Now, the nice thing about this light is that, as you can see from this diagram, the light was produced very early on in the universe, well before any of the complicated astrophysics came about. So we understand the physics of what was going on very close to the Big Bang, in some ways very much better than we understand the physics of what was going on later, because it got messed up by all of this stuff forming and making things very complicated. So in order to understand what we see when we look statistically at the light, we need to understand a little bit about what has happened to the light along the way, because as you see, the light from the microwave background has to pass through all of this universe before it gets to us. And that affects the light in ways which we need to compute. And essentially, the controlling force is gravity along the way. And it's Einstein's theory of general relativity, which we think is the correct one for treating this. So general relativity is split conceptually into two parts. There's one that says that matter tells space or space-time how to curve, in much the same way as if you have a rubber sheet and you put a heavy ball on it, then the rubber sheet will get distorted. Space-time gets distorted by the presence of mass. And the other half of general relativity is that the space-time tells matter how to move. So if you're in this space-time, then any light, for example, from a distant star that's in this curved space-time will have its trajectory bent so that you will see the object not at position A, where it actually is, but at position B. This is a lensing effect, which was detected for the first time in 1919 by Eddington and collaborators, who looked at stars behind the sun. They made observations when there was an eclipse, so that the light from the sun was blocked out, so you could see the stars behind. And this is a composite picture of the positions of the stars when the sun was nearby. So the light has got bent, and the image of the star appears not in the right place, but slightly further out. And it's a composite picture of that, and another picture taken when the sun and the moon had been allowed to move to one side, so that they were out of the way. Now, this is, if this was the signal that you were expecting to see, it would have been a very easy experiment to do. In fact, this has been, the differences here have been multiplied by a factor of 50 by the BBC, so that you can see them. So it's a much, much more challenging measurement to make than it looks like there. But this really established Einstein's general theory of relativity as being favored over Newton's, so much so that Einstein was very tickled by this and wrote a postcard to his mother, which is reproduced here. It's in German, so I'll translate it for you. It says, "Dear Mother," unfortunately, I don't speak German, so... So this is the picture that we have when we look at the microwave background. We're looking at basically a background light source which has passed through the universe between us and the places where it was emitted. And this is just showing the development of structure over the time period since the light was last scattered. And you can see, as time goes on, the structure developing. And the light that we see has taken a slightly tortuous path through this matter, being bent by gravity by the structures along the line of sight. And you'll see some highly exaggerated light paths, the light gets bent by something like 1/30 of a degree, typically. So very small deviations in the direction. But those small deviations in direction are enough to make the background light distribution not genuinely random. So if we want to test whether the original fluctuations were random ones from quantum fluctuations, then we have to take into account the non-randomness which is introduced by the passage of the light along the line of sight. So we have that bending by gravity. There's also another effect which is illustrated in the top left panel here, that as the light passes through the matter, if it passes through a rich cluster of galaxies, that's a deep potential well where the light will gain energy as it falls into the well and then lose energy as it climbs up the other side. So in normal circumstances, those two would cancel out, but if the gravitational potential evolves with time, then, oops. Sorry, Dave, that was supposed to be coming in a moment. If the gravitational potential evolves with time, and you can see it in the picture evolving with time, then the two effects don't cancel out. So this effect is called the integrated Sachs-Wolf effect. And this combination of bending of light and the integrated Sachs-Wolf effect introduces a level of non-randomness that we have to account for. And with the Planck satellite, we were able to detect for the first time this effect. And the way that we can be absolutely sure that this is the effect that we're looking for is to devise statistics which are designed to look for it. And my colleague Deepak Munshi, who's here, and I started to look for statistics which would pick out this signal. And Deepak came up with the answer, which is this statistic which is plotted here. It's called the skew-CL statistic. And what you can see is that the data points here agree with the theoretical expectation which is given by the line. Now, the signal-to-noise of this measurement is not incredibly high, but you can show mathematically that it's the best that you can do. You cannot do better than this. And the good thing about it is that, as was once said about Marilyn Monroe, it curves in all the right places. So it is a mildly significant detection. It's not absolutely set in stone, but we can't do better because we only have one universe. Right? My colleague Dave Clements has many universes, but he bought them. We only have one, and that is a fundamental limitation that we will not be able to improve this detection. It's the best that we can do. But at least we know we've done as good a job as can be done with the universe that we have. Another thing that messes up the randomness of the light is that the radiation that we see includes not just the light from the Big Bang, but there are also sources of radiation at the same frequency which are dotted along the line of sight. The very bright ones can be removed, they can be detected and removed, but there will always be some faint ones which we don't exactly know where they are, but which are contributing a little bit of light to various places in the map. And we can detect those statistically. We can't detect individual ones by another variant of the skew-CL statistic, and that's shown at the bottom here. And again, the data and the line agree very nicely. And there's really no freedom in this theoretical line other than moving it up and down. And it has the right shape. So we're confident with both of these that we've detected the two main effects which affect this particular statistic. It's one again based on the bispectrum. So I was really pleased when this graph came out of the computer. So everything else, sorry, I think we may see Dave again. Everything else, if you take away this randomness, then what's left is consistent with being random fluctuations. And it's important for two reasons. One is that you might be worried that the data processing removed any randomness, non-randomness that was there, And what you're able to show with these statistics is that, no, the instrument is working extremely well. The data processing is working extremely well because it is preserving this low level of non-randomness that we expect from these things along the line of sight. So we can also be confident that it hasn't destroyed any non-randomness from the early universe, and we can be confident that everything else is consistent with being random. So the early universe is in good shape. Planck was done by a lot of people, those people. So let's now turn away from the early universe to look at the behavior of the late universe and see what questions we're now trying to address. The part of Einstein's theory that says that matter tells space how to curve is represented by this very elegant equation. I've been a bit loose in my definitions of pi, those specialists will recognize. But just to keep things simple, it's basically just an equation that says G equals T. These things should be regarded as symbols rather than numbers. So essentially, the universe is controlled by G and T. And that's a feeling that I can identify with. And what Einstein did when he introduced the cosmological constant was to add a slice of lambda, like this, and ended up with this, what I think you'll agree is a slightly more ugly equation to be the equation controlling the universe. Einstein himself described it as such, as an ugly equation. And there is a possibility that he was perfectly right, and this is really the equation that controls gravity. What it amounts to, conceptually, is that he changes the law of gravity so that the gravitational parts on the left-hand side get changed. So T is the source of gravity. For physicists amongst you, this is the analog of Poisson's equation, del squared phi is 4 pi g rho. So the things on the right-hand side are the sources of gravity. The bit on the left-hand side is the effect that those sources have on the space-time of the universe. So one possibility is that this is absolutely right, that Einstein was right, and that's the end of it. It's a bit of a puzzle why it looks like that in a slightly ugly way. These days, we would probably look to modify it in the other way by putting the lambda on the right-hand side of the equation. Now, if you do that, lambda then becomes a source of gravity, and you can interpret it as a new form of matter. And it's in this form that this looks like the thing which is called dark energy. And specifically, it corresponds to a positive energy of the vacuum, that the vacuum has a certain energy density. It also has some rather strange properties, such as a negative pressure, and it also has this repulsive gravity that's required to accelerate the universe. So one possible modern interpretation of Einstein's cosmological constant is as a new source of matter. And if you do that, then this then just ends up looking just like Einstein's original very beautiful equation. It's just that there's another component of matter. The matter here included in T already includes several components, matter, radiation, and so on. So you're just adding something new to it. It turns out to be a very strange new thing, but it's just another new thing. So some of the things that we're trying to do today are to really understand whether this new piece is really a vacuum energy or whether it's a new field. The other possibility is that the left-hand side of this equation gets modified by a different law of gravity. So areas of active research concentrate on either modifying the left-hand side in a different way from Einstein's or by looking for the properties of the new stuff that appears on the right-hand side. So dark energy is one possibility. It doesn't necessarily have to be a vacuum energy. A vacuum energy will have a constant energy density as the universe expands. If it could be something else, it could be a new field whose energy density changes with time. But if it changes with time in a slow enough way, then it can look very much like the universe that we see. We don't know a great deal about dark energy. There's a couple of theories. One is that it's a plant nutrient. You can buy this. I have one of these. Another more interesting possibility is that it's a beer with 4.9% alcohol. Now, Now, this is a beer drinker's delight, because if it's in the form of the right-hand side, then as the universe expands, then the universe just makes more beer. So this would be ideal. So the most exotic possibility for accounting for the acceleration of the universe is that the law of gravity is changed by the universe having more dimensions than we think it has. So we're used to having 3 spatial dimensions plus 1 time dimension. But there are theories, particularly those based on string theory, that suggest that we live in more dimensions than we think. And if that's the case, then there's the possibility that the gravity will, in some sense, leak out into the bulk. We live on a 3 plus 1 dimensional subspace of the total, and the gravity can leak out into the other dimensions and change the form of the law of gravity on large scales in our own universe. So that has the exciting possibility that by making measurements in our own dimensions of the universe, we can deduce that there are extra dimensions that would otherwise be perhaps difficult to find. So how would we do it? Well, we can test the gravity law, and we can test the properties of dark energy by looking at gravitational lensing. The effect of the gravity law and dark energy is the following, that it affects the expansion rate of the universe. The history of the universe is altered slightly. It affects the rate at which structures grow. So you've seen the videos of the structures forming. That the rate at which that clumping takes place is sensitive to the law of gravity. It's also sensitive to the properties of dark energy. And it also, if you change the law of gravity, then you can also change the way in which light gets bent by matter. So all of these things affect the images of distant galaxies because they, like the light from the microwave background, has had to pass through the clumpy universe on the way. And if you look at distant galaxies in this extreme case where there's a rich cluster of galaxies in between, then the light from the very distant universe, distant galaxies, has got distorted out of all recognition. You hopefully will be able to see these very thin arc-like structures. Perhaps it's more visible on the one on the right. There's a very long arc here. That's an ordinary galaxy which is beyond the galaxy cluster, but as the light has passed close to the galaxy cluster, it's got bent by gravity, and there are other ones that you can perhaps just about make out here, down here, and so on. So this is an extreme example of light from distant galaxies which has got distorted. What we're more interested in, because these are rather rare objects in the galaxy clusters, are the small distortions that every single distant galaxy will suffer. And if you look anywhere on the sky, if you look at distant galaxies, then their shapes have been distorted by of the order of 1 or 2%. If you can see enough of these and look for the distortion patterns, then that can tell you about the intervening matter between the galaxy and ourselves, which tells you about the structure and the growth of structure. It tells you about the way that light has been bent by matter. And with colleagues, principally Tom Kitching, who's also here, we've been, again, designing statistics that try to get as much out of the data as possible. For these galaxies, we have distance information, so we have a 3-dimensional map of the distortion pattern. So unlike the picture that I showed you before, which was looking at the 2D surface, we do things in 3D, and these are some of the statistics that we use. So that's something that we've been doing with the Canada-France-Hawaii telescope recently, throwing up some interesting things which we don't quite expect. It seems that the matter on relatively small scales is not behaving quite as we expected, and we're trying to think of new statistics which will tell us a bit more about what's been going on. So one possibility is that the matter has been moved around by injections of energy into the universe by active galaxies, by black holes. Another possibility is that we're perhaps seeing signs of non-zero neutrino masses, which can alter the distribution of fluctuations by a small amount. We don't know yet what the quite what the effect is, and probably with the existing surveys, it's not possible to do anything very precise. But in the relatively near future, there'll be a telescope put in space which will map out the distant galaxies exquisitely well, and that's called Euclid. And the statistical power of surveys taken by a telescope like this are very great. So this is our hope for detecting differences from Einstein's gravity, or detecting whether the dark energy is really Einstein's cosmological constant or not. At the moment, it seems that Einstein was right. There's no serious evidence against Einstein being right. What I'd like to do in the last few minutes is to change tack completely. Many of the analyses that I've shown you have involved taking reasonably large data sets and boiling them down into learning something about the universe, but we're generally boiling the data down to a few numbers. So we take a reasonably large data set and try to learn a few things from each data set. That's a very common problem. I wanted just to spend a few minutes talking about what we've been doing to apply that sort of technology to a different field. That of medical image registration. So here is an example of half a head, which has been scanned with an MRI scanner. So the sort of typical size of the data set here is you might have 100 slices through the head, each of which is a 512 by 512 pixel image, make it up into a 3D volume. That's about 26 million voxels, 26 million items of data. And if you think what a medic might want to do with something like that is that if you've had a scan and then a problem has been identified, you have a scan sometime later, and obviously the clinician wants to see if anything has changed. Now, in order to do that, you need to look at the same place in both images. So the next time the patient goes into the scanner, the position of the head's going to be slightly different, so you have to line them up. So here the problem is you've got 26 million items of data. You want actually 6 numbers. For a rigid body, there are 6 numbers you need. There's 3 rotations and 3 translations, up, down, and forward. So similar sort of problem. Can you do it very fast so that the medic spends most of the time actually looking at the feature of interest rather than trying to find it in both images? So we adapted some techniques that we used for galaxy spectra to do this, and in fact my postdoc Ben Panter has spun out a company to do this. For the head, it's relatively easy. It's just 6 numbers. There are other parts of the body which are much more challenging. These are lungs. They don't move rigidly. In this case, if a rigid transformation is the right one, then it's too late. So these are non-rigid transformations, much more challenging. And you can see what I hope you can make out, that there's a cursor here, which when you click it on one of the images, it highlights on the other image the same feature. So here's another one with four different historical images. So you click somewhere up on the top right, and immediately on the crosshairs, that lung nodule is highlighted. So the medic can spend all the time actually investigating that, rather than spending a lot of time scrolling through each of the previous images to try to find the blessed thing. And as you can see, they're not easy to find, these. So this company is still going. It's just had its first major contract to sell to hospitals in the USA. So I just wanted to finish to say that I've been trying to give you a little bit of a flavour of the sorts of things, some of the things that we do at the ICIC in learning stuff from relatively large amounts of data. And just to finish, I'd just like to say thank you to all of my collaborators, the ones who've contributed most to the stuff that I've shown you today are given here, but there are many others, some of whom even collaborated more than once. And finally, to my long-term collaborator and friend, John Peacock, who's also been an inspiration to me over the years. Thank you.